Rocks are storytellers of the past. Igneous rocks tell us about volcanic activity and conditions deep within the earth. Metamorphic rocks tell us about the movement of tectonic plates deep within the past. And sedimentary rocks tell us about past environments, climates, and biodiversity at Earth's surface. This is a sedimentary rock. Have you seen one like it before? Do you notice these interesting markings? This rock certainly has a story to tell, so let's see if we can discover it. So we talked about how sedimentary rocks record evidence of different environments on Earth's surface. But how does this work? Well, different environments like rivers, deserts, or glaciers have very different sedimentary processes that act within them. For example, rivers carry sediment by water, deserts carry sediment by wind, and glaciers carry it by ice. These different processes create diagnostic features in the sediment when it's deposited, and are then left behind in the rock record after the sediment is buried. Today I want to take you to one of my favorite sedimentary environments. Rivers! Rivers are such dynamic environments. They're constantly changing, moving, and rearranging themselves. And because of this, they leave behind some fascinating formations in the rock record. These are called bed forms because they form at the bed of the river where the water interacts with the sediment. There is a sequence of bed forms associated with different flow velocities of a unidirectional current. Lower flow regime bed forms form under slower or subcritical flow. These include lower plain beds, which look like flat, tabular surfaces of sand or mud, ripples, and dunes. Upper flow regime bed forms, which form under faster or supercritical flow, include upper plane beds, which are typically made of coarser grains than lower plane beds, like gravel or coarse sand, because the water's moving faster, and therefore it's able to carry and deposit larger pieces of sediment. We also find anti-dunes, which are very unusual bed forms that actually migrate upstream under very fast flow conditions. Let's take a look at some of these bed forms. Here are some ripples. Notice how they are asymmetrical. They have a long Stoss side and a steep lee side. They form as the water flows over the sand, transporting the grains in the downstream direction. And so the long Stoss surface of the ripples points in the direction of the current. So, what might this look like if we came back here 100 million years from now? Well, it might look something like this. This sandstone shows a cross-section of ripples migrating under unidirectional flow. These diagonal lines are the steep lee sides of ancient ripples. The lines are called foresets, and they record the ripple migration in the downstream direction, which would be this way. So by looking at this rock, we can tell which direction the current of an ancient river was flowing, which can help us to reconstruct the ancient environment of an area. Sedimentary rocks also preserve skeletal fragments, or body fossils, that can give us a clue about what kind of life forms were present in these ancient environments. This is a carbonate rock with some marine shell fossils. Other kinds of biological clues can be left behind in the rock too, like these dinosaur footprints found in mud rocks here in western Massachusetts. What about this one? Can you guess what made these imprints? They're raindrop impressions in mudstone. This rock has captured a rain shower that happened 200 million years ago. Isn't that incredible? Sedimentary rocks are wonderful storytellers of the past. So the next time you see a rock like this one, don't just take it for granted. It's a clue that you might be standing in an ancient riverbed.